Let's move on now to the concept of polarity and the molecular structures that result in polarity. The bond angle is the angle between any two bonds that include a common angle. The bond distance is the distance between two nuclei of two bonded atoms. The bond distances or lengths and angles are shown above for formalin, the formalin molecule or formaldehyde. And here it is. What you can see is that the bond distance between carbon and oxygen is 1.21 angstroms. The angle between the two hydrogens is 118 degrees. And I'm going to show you in the next several slides how these various distances and angles are measured, or not measured, but found. The way that the molecules arrange themselves is according to a theory known as the valence shell electron pair repulsion theory, or VSEPR. This is the theory that states that the structure that a molecule will form will occur to minimize the repulsion between electron pairs by maximizing the distances between them. In other words, you have pairs of electrons that are constantly moving around in the molecule, and the arrangement that a molecule will take of its atoms will result in such a way as to maximize the distance between these repulsive pairs, they all having the same negative charge. So for example, you have beryllium fluoride, and beryllium fluoride has an angle of 180 degrees to maximize the distance for all those lone pair electrons that are out there. Any structure other than 180 degrees brings those lone pair electrons closer to each other than this structure. So this structure maximizes the distance between those lone pair electrons so they do not interact. Now here is a table that came from your book that shows how these various lone pair electrons are distributed in various structures in order to maximize this distance between repulsive pairs. And so you start out, you have to figure out, and we'll show you how to do that in just a second, how many regions of electron density there are. And if you have two regions of electron density, then you'll form a linear structure that maximizes the distance between those two regions. If, on the other hand, you have three regions, then you will form something that looks like the second column, which is called a trigonal planar structure. And the example is shown BH3, where the angles are all 120 degrees. Four regions results in a tetrahedral structure with angles of 109.5 degrees. Five regions results in a trigonal bipyramidal structure. Remember, these are all three-dimensional structures. And you can see that with the phosphorus pentafluoride. The three fluorines are in the same plane, and then the one fluorine is above and one fluorine below. And then lastly, in the most complex structure where you have six regions, you form an octahedral structure with four fluorines here in one plane, one above and one below, and all the angles 90 or 180 degrees. So this shows, using the VSEPR theory, how to distribute these various zones or regions of high electron density. Now, these zones of high electron density can either be a bond or a lone pair of electrons. So it doesn't have to be an atom sitting up there. It can be a lone pair of electrons sitting up there. And we'll show you how to do that in just a second. So here's an example. This is this is methane. You have 4 regions of high density. So this forms a tetrahedral structure. So the electron pair geometry is the structure that includes all electron pairs. Now in this case, there aren't any lone pairs. All the pairs of electrons are associated with bonds. The molecular structure will show just the atoms involved, does not necessarily show the lone pairs of electrons. So this molecule of methane has a tetrahedral structure. This is the molecular structure and also the electron pair geometry. Both are shown here in this particular situation because there aren't any lone pairs of electrons. Now here's 3 examples, some of which have lone pairs and some of which don't. A shows the electron pair geometry for ammonia. Now ammonia is NH3. NH3, the central nitrogen, has a lone pair of electrons and 3 hydrogens which are arranged inferiorly below and to each side of the nitrogen, which is in the middle. So you have 3 single bonds and 1 lone pair. The middle one is the trigonal pyramidal structure of a compound like BF3 we showed, or BH3 we showed in a couple slides ago. There isn't a lone pair, and so it forms a trigonal pyramidal structure as opposed to a tetrahedral structure because there are no lone pairs. The third one here shows the fact that in some cases there's minor deviations. This is actually a repetition of A, showing that there is a minor deviation from the idealized angle of 109.5 degrees to 106.8 degrees. And this is because the lone pair takes up slightly more space than the bonds do. And so each of the bonds have to come a little bit closer to each other. If there was a hydrogen up there where that lone pair was, then it would be 109.5. Now what this does is it works in what we looked at before and takes into account the possibility of lone pairs. So in the first one, if you have 2 electron pairs and both of those electron pairs are bonding, then you have a linear structure as shown in the first column at the top. In the second, you have 3 pairs of electrons, all three of which in the first one are bonding, so there are no lone pairs. The second one, 2 are bonding and 1 is a lone pair. And you can look at the various other possibilities, and you're looking at first the total number of electron pairs, and then second, how many of those pairs represent a lone pair. And then using this table, you can figure out the various structures that occur and the angles that occur with these structures. You do not have to memorize these tables. If I give you a question or problem, I'll either refer you to a table like this in the book, or I will supply the table. So the first step, when you're asked to tell what sort of geometrical shape a molecule will take, is to write the Lewis structure for the molecule. The second step is to count the number of regions of electron density. These are the sum of the lone pairs and the bonds around the central atom. Now in this case, single, double, or triple bonds all count as one region. And then once you do that, you know how many pairs you have and how many lone pairs you have. You use a table like the last slide in order to determine what the shape is, which is given linear, trigonal planar, tetrahedral, etc. If more than one arrangement seems to be possible, then you want to select the arrangement that minimizes the repulsion between electron areas of electron density. So let's look at the electron pair geometry, or the molecular structure of carbon dioxide. The first thing you have to do is write a Lewis structure for carbon dioxide. And that's this one. Now notice, when you look at the carbon-oxygen on either side, you have one bonding pair. You have one bond and two lone pairs. Each double bond represents one electron region. So you have two electron regions for the two double bonds and two lone pairs on each side. So the VSEPR would indicate that this is a linear structure. With BCl, you have this Lewis structure, BCl3. In this case, you have one electron region for each bond. There's no lone pair on the central atom, and therefore the structure is going to be trigonal planar. Now look in the book and make sure you understand you have three electron regions, no lone pairs, so your geometry is trigonal. And the electron structure, or the molecular structure, is going to be the same because there are no lone pairs. Now this is the ammonium ion. So we write the Lewis structure for the ammonium ion, and it looks like this. There are no lone pairs, and you have four regions. So this is going to be a tetrahedral. Four regions without a lone pair. So it looks like this. And the molecular structure looks identical to this. So the electron pair geometry and the molecular structure are both tetrahedral. Here's water. You write the Lewis structure for water, and you notice that you have two regions for bonds and two for lone pairs. So you have four regions. So your electron structure is shown on the left here, electron geometry, and your molecular structure is shown on the right. So there are four regions of electron density, so it's a tetrahedron for the electron pair geometry, and because two of those are lone pairs, then the molecular structure is a bent structure where the angle will be 109.5 degrees. Now let's look at one that's a little more complicated. So how do you do something that looks like this? Well, the first thing you have to do is draw a Lewis structure, which has been done for you here. Then you have to consider each central atom, which reading from left to right would be nitrogen, carbon, carbon, oxygen. You have to consider each of those independent of each other. So in the nitrogen, the first nitrogen, you have three bonds and one lone pair. The second one, you have four bonds. The carbon with two hydrogens, you have four bonds. The CO, you have 3 bonds, no lone pair on the carbon, which is the central atom. And then lastly, you have 2 bonds and 2 lone pairs on the last one. So NH2, 3 bonds, 1 lone pair, so that part of the molecule is going to be trigonal pyramidal. That lone pair on the nitrogens on the left there is shooting straight up in the air, north. The second one is just going to be tetrahedral. 4 bonds. The next one is 3 bonds with no lone pair, trigonal planar. And then lastly, you have 4 with 2 lone pairs, so that's tetrahedral but bent in terms of its molecular structure. Those 2 pairs of lone pairs fill out the rest of the tetrahedron, but you don't draw that because this is the molecular structure for this molecule.